Suppose every component of y is integrated of order 1, meaning its first difference is stationary. The components are co-integrated when a non-zero vector beta produces a stationary linear combination beta prime y. In a two-variable example, y1 minus b times y2 is the equilibrium error. The co-integrating vector describes long-run relations, but it is not unique in scale. Multiplying beta by any non-zero constant leaves stationarity unchanged. In a rank greater than 1 system, any non-singular rotation of the co-integrating vectors spans the same space. Normalization is needed for numerical reporting and economic interpretation. Rewrite a first-order VAR in differences. The change in y equals a matrix pi times lagged y plus an innovation. When pi has reduced rank r, it can be factored into alpha times beta prime. Beta contains r co-integrating relations, while alpha describes how each variable adjusts to past equilibrium errors. This is the core error correction idea. Short-run changes respond both to recent changes and to deviations from the long-run relation. A negative loading in one equation may pull that variable back after a positive equilibrium error. The sign has meaning only after the co-integrating vector has been normalized clearly. The Granger representation theorem connects three views of the same system. A co-integrated process has a vector error correction representation, stationary co-integrating combinations, and a decomposition into common stochastic trends, plus transitory stationary components. With n variables and rank r, the system typically has n minus r common trends. The theorem requires more than a rank statement. Unit roots and stable roots must satisfy appropriate conditions, and the long-run directions must be non-redundant. Its message is conceptual. Permanent shocks move the common trends, while adjustment mechanisms keep selected combinations from drifting without bound. Co-integrating regression can estimate a long-run coefficient unusually quickly. If one integrated variable is regressed on another and their error is stationary, the slope estimator can converge at the sample size rate rather than the usual square root rate. This property is called superconsistency. Superconsistency does not justify ordinary t-tests. The limiting distribution involves functionals of Brownian motion and is generally non-standard. Serial correlation and contemporaneous correlation in the innovations also affect inference. A precisely estimated long-run slope can therefore coexist with invalid conventional standard errors and critical values.